Okay, let me discuss the contents of this video tutorial first. First, I will introduce the topic. Then I will discuss that how you can find the gradient of an image. And then we will see that how we can construct the histogram, I mean getting the bin values from this gradient image. And then I will explain that how we can make the blocks from these cells. And then we will see the block normalization process. And in the last we will see that how we can construct the HOG feature vector from these blocks. And then I will discuss the MATLAB code for finding the HOG feature of the images, and then in the last I will discuss one Python code for finding HOG feature vector. So now let me start this topic. So first let me introduce the topic. The HOG feature, which is actually the histogram of oriented gradients, is a feature descriptor that is used in the computer vision and the image processing for the purpose of the object detection. It's a very popular. So the technique counts actually the occurrence of the gradient orientation in the local portions of an image. So this method is quite similar to that of edge orientation histograms or scale invariant feature transform, I mean the shift descriptor, and the shape contacts. So the concept was first described by the Robert McConnell in 1986, and in year 2005 the uses of this HOG became widespread when the Navneet Dalal first introduced this HOG feature in his PhD thesis under the bell Triggs at National Institute of the Research in Computer Science and Automation in France. Now let's see the overall scheme of HOG feature computation. So first we have the input image segment of size 128 by 64 pixels, and then first we find the gradient of this image segment. So we have two matrices, one representing the magnitude of gradient and other is representing the angle theta. So from these two matrices we get the cells. I mean we divide these two matrices in 8 by 8 cells, and from these cells we find the histogram. We get a 9-point histogram from each cell, and then we group these cells in 2 by 2 manner to form the overlapping blocks, and from each block we get a feature vector. So it's a 36-point feature vector, and then this feature vector is normalized in value, and from all the possible blocks in this image segment we collect all the feature vectors, and by concatenating those feature vectors we get the final HOG feature vector. So let's see these steps one by one. So first let's see how we get the image segment. So suppose I have one image like this. It is shown of size, let's say m by n. So if I want to find the HOG feature of this, first I have to define this window of size 128 by 64 pixels. So I will slide this window all over the image to get the HOG features. And if my object is to get the object detection, then I have to cover all possible scales, I mean the resolution scales of this image. So for that I will reduce the size of this image so that my object of interest can fit inside this window of 128 by 64 pixels. So I can further reduce this size till my object of interest well fitted inside this window, as here you can see. So in this case I will extract this 128 by 64 image segment, and this image segment will be used for the HOG feature computations. So that is done for the case when the object detection is my objective. So now the next step is to find the gradient of this image segment. So here you can see that for this image segment I get the gradient of this image segment. So I have the two matrices. One is representing the magnitude of the gradient, and second one is representing the angle orientations of this image segment. So let's see how we can find the gradient of an image. So just consider this 3 by 3 pixel group of my image segment. So for this center pixel, I will find these gradient values in both x and y directions like this. So in x directions, I will simply do these subtractions. I mean, I will subtract 60 from 50 like this. So the value I get 10. So that is represented by the gx. So that is gradient in the x directions, and in y direction I will simply subtract these values for the center pixels. I mean the 128 minus 64 like this. So the remaining value is 64. So this is in the y directions. So the overall magnitude is computed by this equation, square root gx square plus gy square. So that is a total 64.78, and I will also compute the angle, I mean the orientation of this gradient. So that is done by tan inverse gy upon gx. So tan inverse 64 upon 10, so that is 1.4158 in radians and equivalent to 81.12 in degree. So for each pixel, I will calculate all these magnitudes and orientations. So by this way, I will compute or find these two matrices. One is representing this magnitude and other is representing all the possible orientations in this image. So this is how I can find the image gradient. And now my next step is to find the non-overlapping cells in these two gradient images. So this is done like this. So this magnitude image, gradient image, and the angle gradient image, I will divide these two images into 8 by 8 pixel cells. Okay. Although we have the freedom to decide this size, for smaller images we can go to 4 by 4, even 4 by 4 or 2 by 2 pixel cells, and for large images we can go to the 16 by 16 or 32 by 32 pixel group. So that depends on the size of the image also. Later I will show you during the code execution for different image sizes. I will show the effect of different cell size. And now let's see the important part, that means the computation of the histogram from these 8 by 8 cells. So let's see how this is done. So we actually have the number of bins 9. I mean the length of the histogram is 9 from 0 to 8, and all theta orientations, I mean angle orientations, I am taking from 0 to 180 degree only. So obviously the step size or the bin size is 20 degree and 180 upon 9. And for some jth bin, the boundaries of the bin will be given by this, I mean delta theta dot j and delta theta into j plus 1. So these are two boundaries of any jth bin, and this is the center of that bin. So the center is given by this cj, that is a delta theta into j plus 1 by 2. So by this way I can find the center of the corresponding bin. So this is the overall structure you can see of the histogram. So this is my 9-point histogram. You can see starting from the bin 0, bin 1, bin 2, bin 3 and bin 8. So total bins I have shown like this. So this is my first bin, that is a bin 0. So that's what is shown by the one single color. So these are two boundaries, 0 degree and 20 degree. Okay. And the center is of course the 10 degree. So center is represented by the cj, and the bin boundaries are delta theta into j and delta theta into j plus 1. So that is true for all 9 bins. So here these are the centers of the bin, and here these are the boundaries of the bins. Okay. So now let's see the steps how we can compute this histogram. So what we do actually, first we choose an angle value from the gradient image. Okay. So from gradient angle matrix we first choose the some value of theta, and from that theta we find the value of the bin number, I mean the which bin or bins are to be modified. So that is obtained by this number j and j plus 1. That means for corresponding given angle we have to modify the magnitude of jth and j plus 1th bin. So this j can be found by this equation. So j equal to floor theta upon delta theta minus 1 upon 2. So this theta is your given angle, and delta theta, as I have already shown, that it is a 20 degree, that is the size of the bin. And now what we actually do, once this j is known, then we have the information that we have to modify the contents of the jth and j plus 1th bin. So what we do, for corresponding theta, we have the corresponding magnitude mu. So we will divide this mu into the two parts. Okay, let's say mu1 and mu2. So we will given this mu1 to this jth bin, and we will give this mu2 to j plus 1th bin. I mean, we divide the mu into the two portions, and these two portions will be given to the jth and j plus 1th bin. So let's see how it is obtained. So to the jth bin, the value of, or the portion of the mu, I mean the magnitude, is given by this equation. So this is your magnitude mu, and this quantity inside the bracket will give some fraction, let's say 0.8, 0.6 something. So 0.8 means the 80% of the mu will be given to the jth bin, like that. Okay, and to j plus 1th bin, this is the value, corresponding value that will be given to the j plus 1th bin. And these value assigned to these two bins actually is the bilinear interpolation method. So the sum of these assigned to bin values will always be 1. Obviously, these two portions will sum up to the complete value of the mu. So now let's see one example where the theta is 77 degree, and the magnitude, corresponding magnitude, is 1. So the 77 degree, if you see the histogram structure, you can see that the 77 is lying like this. So it is more close to the bin center, I mean the center of the bin 3. So that's why I have written here that closer to the bin 3. So now let's see how the value of mu, I mean the 1, is distributed to the jth and j plus 1th bin. So first I have to find the value of the j. So I substitute all the corresponding values in this equation. So theta is 77, which is the given angle, and delta theta is 20 minus 1 by 2, and here I am getting this value 3. So it means j equal to 3. So j plus 1 is 4. So it means the third and fourth bins will be modified. So that I have shown, the third bin and the fourth bin will be modified. So by how much value? So let us find the contribution to the third bin. So this V3 will be calculated by this equation, mu Cj plus 1 minus theta upon delta theta. So mu is 1, Cj plus 1, since j is 3, so it is C4 minus 77 upon 20. So what is this C4? This C4 is actually the center of the fourth bin. So here you can see that the center of this bin 4 is 90. So that's why the C4 is 90 minus 77 upon 20. So that is corresponding to 0.65. So it means the 65% of mu will be given to bin number 3. So 0.65 will be given to bin number 3. And now let's see the remaining to the bin 4. Of course, it will be the 0.35, but if you substitute all these values in this equation, you will get definitely 0.35. So that is a mu theta minus Cj upon delta theta. So theta is 77, Cj C3 upon 20. So C3 means that it is the center of bin 3. So this is the bin 3 and its center is 70. So 77 minus 70 upon 20 into 1, that is a 0.35. So your overall magnitude 1 is divided into the two portions, 65% means 0.65 and 0.35. So 0.65 is given to the bin 3 and 0.35 is assigned to bin number 4. So this is how the mu is broken into two parts and assigned to the corresponding bin values. So as I said, this sum of these two values of course will be 1. So by this example we can conclude that if theta is more close to any bin, then corresponding bin will get the more value of mu as compared to the next bin. and that is quite obvious. Okay, so now let us consider another example where the theta is lying exactly at the bin boundary. So this is one example. Let's say if theta is 80 degree, so you can see that theta is 80, which is exactly lying on this bin boundary of bin 3 and bin 4. And again, I am considering that corresponding mu is 1 for this theta 80. So let's see how the mu will be broken into the two parts, and how this bin 3 and bin 4 will get those parts. So let me find the value of j. Of course, j will come out to the 3. So it means the bin 3 and bin 4 will be modified for this angle 80. So the corresponding value which will be assigned to the bin 3 will be found by this equation. So that is mu c3 plus 1 minus theta upon delta theta. So here you can see that there's a c4. So what is c4? That is the 90 center of the bin 4. So 90 minus 80 upon 20, that is a 0.5. So it's quite obvious. If you see the another value, of course that will also be 0.5. So it means the 0.5 is assigned to this third bin and the 0.5 is assigned to the fourth bin. It means if your angle lies exactly on the boundary of the two bins, then the magnitude will be broken into the two equal parts and will be assigned to those corresponding bins in the left and right side bins. So from this you can conclude that if your theta falls on the bin boundary, then the both left and right bins will get the equal parts of the magnitude mu. And now consider another example where theta lies exactly at the bin center. So here I am taking example where theta is the 30 degree. So you can see that this is exact center of the bin 1, and again I am taking the corresponding magnitude is 1. So if your theta is lying exactly at some bin center, let's see how the values will be assigned. So the value of j first we will calculate, and here we get the value of j equal to 1. So it means the bin 1 and bin 2 will be modified. So let's say whether bin 2 will be modified or not. So for that the value assigned to this bin 1 is calculated by this equation. So here I am getting the value 1. So it means that 1 means the whole mu is assigned to the bin 1 only. So there is no need to calculate for the next bin, the bin 2. So if it is lying at the center of the bin, it means the whole value of mu will be assigned to that corresponding bin. So this is the conclusion. If your theta falls on the center of any bin, then the whole value of mu will be assigned to that bin. Okay, so it will not be shared by the two bins. So now let's see how we can make the blocks from these cells. So once the histogram, these 9 bins computation is over for all cells in an image segment, that's 128 by 64 image segment, then 4 cells in 2 by 2 manner are clubbed together to form a block. Let's see how. So see this mu matrix, the gradient magnitude matrix. So this is how we club these 4 cells to make a block. Okay, and this clubbing is done in overlapping manner. That means with a stride of 8 pixels. So this is one grouping. So the next grouping will be this. So here you can see that there is a overlapping, this one. Okay, and next grouping will be like this. So this with a stride of 8 pixels there will be the overlapping between the blocks. So for all 4 cells in a block, let's say you are considering this one block, we have these 4 cells, and for each cell I have already computed one histogram of 9 points. Okay, so 9 points for this, 9 points for this, 9 points for this, and 9 points for this cell. So total 9 plus 9 plus 9 plus 9, the total 36 point feature vector will be calculated for each block simply by concatenating all these values. All these 4 histograms like this. So from B1 to B36. So this FBI is one feature vector corresponding to one block. Okay, so its length is 36. And then once it is done, we will normalize its value by this equation. So here you can see that all values of these feature vectors are divided by this L2 norm. And here epsilon is taken one small number to avoid the divide by 0 values for non-gradient blocks. Okay, so so to achieve this normalization, first we have to find this number k, which is simply obtained by squaring, adding, and then taking square root of all these 36 values. And then once this k is found, we simply divide all the values of these histograms by this k. So this is how we get the magnitude normalization. So this normalization is done to reduce the effect of the changes in the contrast between the images of the same object in an image. So now let's see how the HOG feature vector is calculated after having these blocks. So from each block, as we have seen, that total 36 point feature vector is collected and normalized in the value. So in horizontal directions, there are total 7 block combinations, you can see. So in horizontal directions, there will be total 7 possible blocks in this image segments of 64 128 by 64 pixels. Okay, and in vertical directions there will be total 15 such blocks. Okay, so 7 horizontally and 15 vertically, and from each block I get total 36 point feature vector. So total size of the HOG feature will be 3780 because 7 horizontally, 15 vertically, and then each block has total 36 feature vector size. So the size of the HOG feature is 3780 for this small image segment of 128 by 64 pixels. So of course this is a very huge value for this small image segment, but this is quite powerful and widely used for object detection. Okay, so now let's come to this MATLAB code for getting this HOG feature vector. So first we are reading our image. It may be the grayscale or any color image. Okay, so by imread, this image is going into the img variable, and here cs equal to 8, it means I am deciding the cell size. As I said earlier, that the cell size can be the 8 by 8 pixels. It can be even the 4 by 4 or 16 by 16 or even 32 by 32. So that you can decide in this line. So it depends on the size of the image. Okay, if your image size is very small, then you can go to the 4 by 4, and if your image size is very large, then you can go to 16 by 16 or 32 by 32. It depends on the size of image. And this in this line we are calculating actually the HOG features. So this is the MATLAB inbuilt command, extract HOG features. So here I'm passing the image and then cell size defined by the CS. So if CS is 8, obviously this is 8 by 8 cell size. So I have the two output variables. One is the HOG FB and HOG VIS. So in HOG FB I'm getting the HOG feature vector. Okay, and in HOG VIS I am actually getting the visualization of the HOG feature, so that I can plot later. So here I am plotting all these images and feature vectors. So first I am plotting my input image by IMShow, then I am plotting the HOG features. I mean plot HOG visualization, HOG VIS, I mean this variable, and then I'm showing this image with HOG features by holding on. So here the only input image is shown, here only the HOG features are shown, and here both image and HOG features simultaneously are shown. So let me run this program and where I can show you its performance. So let me jump to the MATLAB. So this is my MATLAB editor and this program is already written. So here first I have chosen cell size 8. So let me run this and I will select a small image. So let me select this image of numeral 4, open it, and this is the output. So this is my input image and this is the corresponding HOG features, and here both are plotted simultaneously. I mean the image and HOG features are overlapped with each other. So now let me run another image. Let me select this image, and this is the output. So here you can see that this image is of large size, and I have chosen the cell size of 8 by 8. So that's why I'm getting this dense, very dense matrix of feature vector. So let me increase the cell size. So by 8 I am taking 16 by 16 cell size. So let me checking this image again. Yes, now I'm getting this feature vector HOG feature. So here you can see that it is quite a good visualization of the HOG features with my input image. So let me take one more example. Here I can take this image, let's say cameraman, and okay, this is my feature vector, HOG feature vector. So input image, HOG features, and both HOG features and image simultaneously in this third plot. So here you can see a good visualization of the HOG features for this input image. And now let me take one color image. So I'm taking this image of this boy, open. Okay, so again you can see the HOG feature for this face. Actually this HOG feature are also used by many persons to recognize the faces, and some also use these HOG features for recognizing the facial expressions. And now let me go for another image. Here I am changing the cell size to 32 by 32, and I'm taking this face. Okay, and this is the corresponding HOG feature matrix, and here you can see a very good visualization of these HOG features on this face features. Okay, so this is my MATLAB implementation. Now let me show you the Python implementation of the same thing. So this is the Python implementation. In Python you must have this library, I mean the SK image. Okay, so from SK image you have to import the IMRead and IMShow just for input and output of your images. And the SK image also has this inbuilt function HOG. So you have to import this HOG computation. And then for exposure, actually for better visualization, I'm importing the exposure from the SK image. Okay, and first in this line I'm reading my input image. So this is the name of your image in your current directory. So I'm show image, that means your image is displayed. And here one variable I have taken AMC equal to true or either false. So AMC actually the multi-channel. So if you are taking the color images as input images, then you have to put AMC equal to true, I mean the multi-channel equal to true. And if your input is a grayscale image, then you have to define AMC equal to false. So this is my function HOG of this SK image library, which is computing the HOG features. So this is your input image IMG, and orientations 9, I mean this is the histogram, 9-point histogram. And here I am defining the cell size, I mean the 16 by 16, 8 by 8, like that. And then I am defining the blocks, I mean cells per block. So this is the 2 by 2, actually the 4 cells in a block. And then visualize true means since I have to visualize the HOG features, so I am making it true, and the multi-channel is equal to your variable MC, which you have defined here. Okay, so for color images it is true, and for grayscale images it is false. Actually here I am setting the exposure value so that you can visualize those HOG features well in the range 0 to 5. And then I'm using this IMShow to showing those HOG features. So let me see the output of this Python program. So let me jump to the Python. This program I have written in the Spider IDE. So this program is already written. I have to just run this program. And here the input image is I'm taking the 3.png. So what is the 3.png in my current directory? So this is the 3.png. So I'm taking this numeral 3 in this case. So let me run this program. Okay, so this is the output of that numeral 3. So this is you can see that how these features are calculated. Okay, and now let me take one more example. Let me take this cameraman. It's a grayscale image actually. Yeah, this is the grayscale image. So since it is a grayscale image, I have to set MC equal to false. Okay, so I am disabling this MC equal to true and then enabling this MC equal to false. And here I will change the name of the image. So this is name of image. There is a cman.jpg. Okay, so this is my input image and let me run this program. Okay, so this is the output you can see for that cameraman for pixel per cell 16 by 16 cell size. So this is how we can compute the HOG features in MATLAB as well as in Python. I have shown you. This is very important feature actually, which is widely used for object detection. So I hope you have enjoyed this video, and in the next video I will try to implement some object detection using the HOG features. So I really thank you all for watching my video. Please like it, share it. Thank you.